Extreme Physics. All right, this is the 1980 AP Mechanics C exam, question 3. This is a billiard ball of mass m and radius r, and moment of inertia about its center of mass is 2/5 mr squared. The ball is struck by a cue stick along a horizontal line through the ball's center of mass, so the ball initially slides with a velocity v0 as shown above. As the ball moves across the rough billiard table, coefficient of sliding friction is mu k. Its motion gradually changes from pure translation through rolling with slipping to rolling without slipping. I have a little video here showing how these billiard balls can do that sort of thing on the table. Here we have a video of a situation that's kind of similar to the AP problem. It's different though. You'll see that they don't hit the ball in the center like they did in the AP problem. And usually you don't in billiards. They hit it low to get a backspin on it. And usually good pool players will either get a backspin or a topspin on something. But in this case, he hit it below the center, which is different, and at an angle. You can see that it's not straight across. It's down at an angle like that. So when he hits the ball, we're going to have rolling with slipping, right? So we got rolling with slipping, and actually it's rolling back. It's actually rolling backwards as it translates forward. So we definitely have rolling with slipping. We have kinetic friction at this point, and then it eventually stops. And we still are rolling with slipping here. This is kind of what was happening in our problem. It was going this way, and it was rolling, but it was also slipping until it gets to the point where there's rolling and no slipping. So if we take a look again, we had the ball going, we had rolling with slipping, and then eventually rolling without slipping. The cue stick hits right in the center, so it's got to be something like that. It's going to hit it right in the center of the... And real billiard players usually don't hit right in the center. Usually they hit the top or bottom, depending what they're trying to accomplish. And here they had the center of mass, and they clearly showed that was like that. And this is the initial translational velocity. And this is radius r. And this had mass capital M. And this was point P. And then it rolled. All right, sometimes it was rolling while it was slipping, and sometimes it's not. So initially it's slipping, but later it won't be. All right. Develop an expression for the linear velocity of the center of mass of the ball as a function of time while it is rolling with slipping. All right. I think I would probably apply Newton's second law for translation here. I'm going to circle. It's after the hit, right? So it's out here somewhere. So I'm going to circle the object of interest and draw a free body diagram. Got something like this. What do we have here? We got y and x. Normal force is acting upward. Normal. And then we have the force of gravity downward, mg. And we have friction. Kinetic. This is while slipping. It's slipping. So that is kinetic friction. All right. So let's take a look. We're going to apply Newton's second law. This is A. Sum of the forces equal mass times acceleration. But we're only interested in the x direction. So sum of the forces in the x equal mass times acceleration. The acceleration is only going to be in the x direction. So what do we have here? We have friction kinetic. I'll say it's negative equals mass times acceleration. Kinetic friction is mu k times the normal force equals mass times acceleration. Let's see. What do we have here? We're going to sum the forces in the y. Sum of the forces in the y equals 0. It's not accelerating up or down. So we have normal minus mg equals 0. So the normal force equals the weight. All right, so minus mu k mg equals ma. Boom, boom. All right, so I guess our acceleration is mu kg to the left, right? Mu kg that way. All right, so that's the acceleration. Now, what can I tell about that acceleration? Well, g doesn't change, and nor does mu k. So therefore, this is a constant acceleration, and we can use the kinematics equations. All right. So I think we'll use this one. We'll say v1 equals v0 plus acceleration times the time interval. All right. So I guess v1 and equals v0 minus. I could have said plus and a negative, but I'm going to simplify. I'm going to say that. There we go. There is our speed of our object as if, forgot the t. All right, so there it is, the speed of our object as a function of time. Develop an expression for the angular velocity omega of the ball as a function of time while it's rolling with slipping. All right, it's rolling with slipping, so there is no direct relationship between v and omega. So we can't say v equals omega r or anything like that because it's slipping. It's slipping. It's rolling with slipping. That's it. All right, so we got rotation now. Now we're going to need some sort of, we're going to need a torque diagram. So I got the thing rolling. I'm going to draw it down here. We got this thing rolling, and the forces on this thing are going to be, so it's going this way. All right, so thing's sliding. We got kinetic friction this way. We got the normal force straight up acting on the surface, and we have, there's the center, and we got the force of gravity down, right? All right, so there we go. Let's see what we got. Let's find the angular acceleration. Let's see, we got some of the torques about the center equals I alpha, about the center. And they gave us the moment of inertia somewhere. All right, so about the center, the only thing acting on the normal force goes through the center, so no torque there. Weight through the center, no torque there. There is a torque due to friction, though, and that looks like it would cause a torque this way, which is a negative torque. So I end up with negative kinetic friction times r. R is the radius, equals a moment of inertia about the center, which is 2/5 mr squared alpha. All right. Kinetic friction is mu k times the normal force, r equals 2/5 mr squared alpha. And we figured out before that the normal force equals the weight. So we go mu k mg r equals 2/5 mr squared alpha. Boom, m's go away. Some of the r's go away. All right, so then what do we end up with? We end up with minus 5 halves mu kg with an r. R. That's not written very well at all. Anyway, there's my alpha. And let's see. Constant. Ooh, that's a constant angular acceleration. Woo! That means I can use the circular kinematics equations. All right. All right, I'm going to use this kinematics equation. Omega 1 equals omega 0 plus alpha delta t. All right. So omega later equals the initial omega, which is 0. When you hit it, it wasn't rotating at all. So we got that's going to be a 0. And alpha is, what do we got? Minus 5 mu kg over 2r delta t. All right. That's what omega is. And yeah, there we go. All right. Let's see. Did I do that right? All right. So there's our, I guess that's the answer to V. So far it's been pretty straightforward. We just applied Newton's laws and for circular and Newton's laws for rotational. And then the problem gets interesting. It says, determine the time at which the ball begins to roll without slipping. Now we need to understand what happens at this point. This is a threshold problem. What is happening when the ball is just transitioning from rolling with slipping to rolling without slipping? All right. Well, number one, if it's rolling without slipping, hopefully you picked up on this one right away, that V equals omega r. Right? V equals omega r when it's rolling without slipping. So this is going to be true. But we need more conditions than that because this won't, there's a whole bunch of times when it's like that. We want to know that moment at which it's just rolling without slipping. So what's going to happen is this is going to be true. But also this is the very end where these two are true, right? Because when it, I know what you're thinking. You're saying, but it's rolling without slipping. And these are rolling with slipping. But this is that no man's land where it's just right at that transition. So these are still true. And so is that. Okay, so it's that moment in time where that rare moment in time when all these are true. So, anyways, that's kind of straightforward once you know that. That's the hard part, knowing that these are true and that's true. Only at that moment. Only at that moment. And so, anyways, so let's just set the V. Well, V equals V0 minus mu K G delta T, right? So really all I'm doing is I'm going to say V equals omega R, right? So V equals, here's V, and here's omega, equals omega, which is minus 5 halves mu K G R delta T. All right. So there you go. And does V equal omega R in this case? Let's see. We have a positive V, right? That's positive direction V. And we're going to have an omega. Oh, it's negative. So V doesn't equal omega. V equals negative omega R. Oh, interesting. So that has to be negative so that when I plug that in there, that's going to be positive. All right. Beauty. And we want to just solve for T. All right. So what do we got? We got V0 equals 5 halves mu K G delta T all over R plus mu K G delta T. All right. What's up with that R? Oh, I forgot my R in here. I forgot my R. I was like, look at it. Wait, how could that be the? Oh, yep. Okay, so this is omega R, right? So here's omega, and then I can multiply that by R. So that goes away. So there we go. All right. I would have caught that with my units. So anyways, so the R goes away. All right. And what do we have? We have, is that 7 halves? 7 halves mu K G delta T is V0. So 2/7 V0 over mu k g equals delta t. All right, there's our time. There's our time. All right, need to be careful. Made a little mistake early. I said V equals omega r, but V doesn't equal omega r. V is positive. Omega would be negative here, so V equals negative omega r. Got to get that in there. This becomes positive, and there we go. All right, so that C was more challenging certainly than the other parts because we needed to realize that this was true and this is true, and there was a direct relationship between V and omega at that point. Those three things were true only at that moment. After that moment, V and omega still have that relationship, but these are no longer true because these are derived from rolling with slipping, and it's not slipping anymore. All right, when the ball is struck, it acquires an angular momentum about the fixed point P on the surface of the table. During the subsequent motion, the angular momentum about P remains constant despite the frictional force. Explain why. Well, let's see. So we got smashed here by the Q stick, right? Here's P, there's point P, and the Q stick's hitting it, right? Like right there. It's going to hit right there. And, well, if we take a look, we see that our friction is going to be that way, right? When it hits, we have the normal force and we have the weight. Well, we can see that about point P, there's no net torque. There's no net torque about point P because friction goes through point P. And so does the normal force and so does the weight. There is no net torque about P, so there's no net torque. So angular momentum is conserved. There needs to be a net torque to change the angular momentum. So there is an angular momentum when this hits, because when this hits, right, when the Q stick hits, it applies a force like that just during the hit, right? That's a force of the Q. It is applying a torque about point P. But as soon as this goes away about point P, there are no other torques. So angular momentum will be conserved about point P. Angular momentum is conserved about point P. When the ball is struck to the surface during the subsequent motion, explain why it's so. Yeah, well, because friction goes through point P, so it can't apply a angular momentum about point P. There you go. That was 1980. Question 3. That was the year I graduated from high school. 1980. All right.
History. Physics.